Okay, we're going to do a short one today. We're going to be looking at page 9, middle of the page, the beginning of the thermodynamics chapter. We're going to be talking about enthalpy today. We started talking about it in class as far as Hess's law is concerned, so actually I jumped ahead a little bit. This should be easier. You can see the Regents font here, so this will be a little bit easier than stuff that you've been seeing recently. A brief review of what enthalpy is. This is not anything too surprising. It's the heat of the reaction. We looked at it. It's one of those 6 magical lines. So what I'd like you to do is I'd like you to draw one of those graphs right here where it says draw an endothermic reaction diagram. So potential energy over here on the y-axis and reaction coordinate here on the x-axis. Draw your endothermic. I'm going to try and resist the urge and tracing out a curve for you. I'm not going to see. All right. So go ahead and draw an endothermic reaction diagram. And then instead of drawing all 6 lines, I just want you to draw the one interval where delta H is located. Just a little bit of review from the early part of this chapter. Okay, we move right on to page 10. And it's time for another one of those lovely field trips without a permission slip. Don't tell your parents. We're going to go to the reference table. So take out reference table I, and you will see we looked at it briefly before. There's table F and G and H. All these tables we know now. It's a good thing it's almost April. Table I is heats of reaction. I'm going to zoom out just a little bit, and you will see all the wonderful stuff that this table gives you. Occasionally, you're going to find that Regents ask you about the enthalpy, or the heat of certain reactions, and you're going to be like, well, how am I supposed to know about that? And they're really giving you a very subtle hint that you should be looking at your reference tables, and table I is a good place to go. Lots of reactions here. Nice little important captions at the bottom. A little asterisk and a little bit of information at the bottom that's even more awesome. It says the delta H values are based on molar quantities represented in the equations. Yeah, blah, blah, blah. But a minus sign indicates an exothermic reaction. That's important, but that's really nothing new. But I thought, you might not like to know that it's there. I think I showed it to you also. But anyway, we're going to be looking at this table right now and looking at what some of these numbers mean. Let's take a look at the first one, just so we understand what the table means. This is the combustion of methane. See, methane, CH4, and oxygen going to CO2 and water. And you will see that this indeed releases energy. You see the negative sign right there. Not a shock. You're burning methane. This is actually the reaction that occurs in our Bunsen burners. And it releases 890.4 kilojoules for every mole of methane. I guess in the octane equation, the one right here, this negative 10,943 is for 2 moles of octane. That's what the first line of this caption means. Just talking about the fact that it's the molar quantities represented in the equation. This is octane. This is stuff in gasoline. Look at all the heat that it produces. Not surprising we use it as a fuel, right? So anyway, we're not going to be talking about these 2 combustion reactions today. Let's go to the notes and see what it asks about. All right, what does the sign of delta H tell you? Oh, all right, so you got to fill this out. You're going to do this on your own for homework. Positive delta H means what kind of reaction? That's an endo or exothermic question. Negative delta H means nothing terribly new here. So from that, you should be able to tell me whether the reaction of 4 aluminums and 3 oxygens to make 2 aluminum oxides is exo or endothermic. You might be thinking, what? How am I supposed to know? Remember, go to table I. I told you. Anytime they have an equation like that, you're not supposed to know. It's right here. Okay, so I'm not going to tell you the answer. I need you to write it in for homework, but that's where you've got to look. We're going to focus on this equation right now. All right, the delta H I'm going to look up. Negative 3,351 kilojoules. All right, let's write that in. Now, I'm going to get a little tricky. Look at this equation. Now, what would happen if I only used 2 moles of aluminum? Look at how many moles of aluminum, wink, 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 hint, hint. How many moles of aluminum are used in the equation in the table? Now, what if I used only 2 moles of aluminum? What would the delta H of that reaction be? I need you to write that down for homework. Not a tough question, but it's important to be able to recognize what happens if the moles are different than what's in the equation. What do you do? What happens if I switch the direction of the reaction? Instead of going 4 aluminums and 3 oxygens goes to 2 aluminum oxides, what happens if, I know it's not on your notes, you can write it down, what would be if we did this? Go back to the original one, not the one that I just had. Let's see. 3 goes to Yes, that's right. If you do 2 dashes and a greater than sign, it magically turns into an arrow. It's good stuff. Goes to 4 aluminums and 3 oxygens. Okay. So if I switch the direction, what would the delta H of that reaction be? All I did was switch the reactants and the products here. It's an important thing to note. You may remember from class today, we talked about it during Hess's law. What is the change in enthalpy for this reaction? I'm going to be more specific here. Sorry about that. I forgot to mention. Let's do it with water gas. 2 water gases go to 2 H2s and an O2. What's the delta H for that reaction? Again, that's homework. Another way to write this, I'm just reading what I wrote, is to have the energy directly in the equation. See, you could write 4 aluminums and 3 oxygens goes to 2 aluminum oxides plus heat. Heat being a product means that heat is given off. Okay, so that's heat as a product. If it were absorbing heat, you'd put heat over here. You could also write it like this, or 4 aluminums and 3 oxygen goes to 2 aluminum oxides plus 3,351 kilojoules. Now you may be saying, well, wait a second, didn't we just write that it was negative 3,351 kilojoules? Yes, but do you remember? There's no such thing as negative energy, okay? Negative sign just refers to the fact that it's giving off the heat. If you're going to put it in the equation, it's just a quantity. It's aluminum oxide and the plus sign and 3,351 kilojoules of heat. So with that in mind, what you've got to do on page 11, there are 3 examples here. I need you to rewrite these equations just in the space below, but add the joules of heat, not just the word heat, but the joules of heat on the proper side of this equation, and that equation. And if you don't know what to do about that, because you don't know about these equations and what their delta H's are, watch the video again. You should know where to look to find the delta H's for this now. But anyway, I want each one to look something like this. It won't be exactly like this because the equations are different, but something like this format for these 3 equations. If you want to fill out these last 2 blanks, that's fine. You'll notice that if reaction is exothermic, heat goes on one side, and if the reaction is endothermic, the heat goes on the other side. Not a big shock there. You'll figure out which side's which, and then you'll be in business. So that is all I need you to do tonight. Thanks.